Okay. So yesterday we started off by looking at concepts in vector space. We'll see what a vector space is a little later. We defined what we will refer to as n vectors. Which is simply an index list of numbers, and then we talked about what we mean by the size or dimension of an n vector, and we also talked about equality between two n vectors. And we said n vectors are numbers of the set R power n. Okay. Continuing further, we will now define some standard n vectors that we will often come across. So, some of the standard vector we will come across is the zero vector. Okay. When I say zero vector, that simply means all the elements of zero, like here. A zero n vector would mean simply a column of all zeros. One vector, on the other hand, would mean a column of all ones. Okay. Unit vectors, on the other hand, are expressed as E subscript something, E subscript I. Okay. In our case, a unit vector would be something where all the elements are zero except for one element, which is equal to 1. Okay. And the subscript tells you which index has a non-zero value, essentially 1. Right? So E1 would mean the first element is 1, everything else is 0. EI would mean everything is 0 except for the ith element, which will be 1, and everything below that is also 0. Okay. That will be a unit vector. How many possible unit vectors can we have in Rn? For example, if I have the set of n vectors, right? How many possible unit vectors can I have? 1. Can I only have one unit vector? Okay. Let's talk about R2, right? R2 would be vectors of this form. Some element here, some element here. Essentially, index list of two numbers. How many possible unit vectors can R2 have? 2. Okay. What are the 2? You have to be louder so that I can hear you. Yeah. 1, 0. And 0, 1. What about R3? How many possible do we have? 3. It's 1, 0, 0, 0, 1, 0, 0, 0, 1. Similarly, Rn would have n unit vectors. Now, we've talked about vectors as vectors simply as numbers, right? It turns out that we can associate geometry with these vectors. Okay? We can always think of n vector, let's say V, from the space Rn, as an arrow starting from some point 0, which is essentially the zero vector. Okay? Ending at the point corresponding to the vector V. For example, if you have R2, which is a plane, right? You choose some point, let's say this is my R2 plane. You choose some point arbitrarily, that's you're free to choose, so, as the zero vector. Once you've chosen the zero vector, every other R2 vector can now be represented by an arrow with a certain length and pointing in a certain direction for every other R2 vector. For example, maybe 1, 0, one of the unit vectors could be this. Okay. 0, 1 could be this. If you say 2 minus 4, that could be this, so on and so forth. Which essentially means all of these R2 vectors, vectors from R2, and points in this plane. If you choose any one of these points is 0 arbitrarily, then every other point can be represented by an arrow starting from the 0 vector to the point corresponding to each of those vectors. Right? And this is often a useful way to think about it, because later on we'll see that many of the algebraic operations in linear algebra can be thought of as simply manipulating vectors in Rn. Okay. So with that in mind, so we've defined our vectors or n vectors so far, and we've also now associated a geometrical entity to these vectors, simply arrows. So vectors are simply points, or vectors are simply arrows in some space with an arbitrarily chosen 0 vector. Okay. Turns out there are two useful operations you can define on vectors, n vectors at least, right? One is called vector scaling. Okay. The other one is vector addition. We'll come to vector addition after this. We'll first look at what is vector scaling. Okay. Algebraically, vector scaling is simply multiplying a vector by a scalar. Okay, written like this. So the vector, you have a vector v, and you generate a new vector called w by simply multiplying v by some scalar alpha. Okay, and what that means is not what it means to multiply two real numbers. Okay, now when I say multiply a vector with a scalar, it might not be immediately clear what that means. Okay. And the definition of the scalar multiplication or vector scaling is given here. You simply take each of the elements in your vector, okay, and multiply each one of them by the scalar alpha or a in this case. Okay, that's the definition of how you scale a vector by a scalar. Okay, where if you take a vector from R2, let's say you take -2, 4. So I call this the A vector. If I say I want to scale this by 5.1, okay, then I simply say I'm doing this operation. And when you say you're scaling a vector, all you're doing is you're multiplying each of the elements of A by this scalar. Okay, so this will be 5.1 multiplied by -2, 5.1 multiplied by 4. So that will simply be -10.2, 20.4. Okay. This is the algebra. Geometrically, what this simply means is if you have a vector A, that would be, so for example, let's say you have a vector V, there is this black colored vector. Right? When you say you're doing vector scaling, all you're doing is you're not changing the direction of the vector, you're simply taking the vector and you're either stretching it, compressing it, or you can also reverse it. For example, if I multiply the vector by 1, the number 1, then I'm not doing anything to the vector. If I multiply it by a number larger than 1, then I'm essentially stretching the vector. If I multiply by a positive number less than 1, then I'm compressing the vector. If I multiply it by 0, I'm shrinking it to the origin of the 0 vector. If I multiply it by a negative number, then I'm simply flipping the vector and making it point in the opposite direction to the original direction it was pointing to. Right? That's what I've shown here. So I take v, if I multiply v by 0.7, the vector is shrunk. If we multiply the vector v by a negative number, you essentially flip direction. And depending on the magnitude of the scalar that you've used, the length of the new vector could be larger or smaller than your original vector. Because I multiplied the -1.1, this red colored vector, of course, looks like it's slightly longer than the original vector v. Right? So one of the most important operations that we will deal with when we're dealing with vectors is vector scaling, and this is the corresponding geometric operation that is associated with it. We'll look at some basic properties. Again, for now, think of all of these as real numbers. The vectors are real numbers and the scalars are also real numbers. Later on, we'll see that the vectors will have complex numbers and the scalars might also be complex numbers. So these are all properties satisfied by vector scaling. The operation is commutative. That means alpha times v is the same as v times alpha. The order does not matter. It's associative. this, and then it's also distributed. These are again obvious because these are simply properties of real numbers, right? So we don't have to think too much about that. The next operation we'll define, a very useful operation, is called vector addition. In vector scaling, we had a scalar and a vector, and we were somehow combining them. In vector addition, the input to the operation are simply two vectors. Okay? And this one. Okay. Okay. So when we had vector scaling, there were two inputs to this. One was a vector from Rn, and the other one was a scalar. Okay? And what we got out was vector addition. On the other hand, I'm going to call it VA. It takes two vectors, V1, V2, and both these vectors have to be from the same space. That means in this case, we'll assume both V1 and V2 are from Rn. You cannot add a vector from R2 and R3. The vector addition operation is defined only for vectors from the same space. Okay? And R2 and R3 are different spaces. Okay? So if we had two vectors U and V from Rn, U is given like this, given by this, V is given by this. This addition operation, you simply do element-wise addition. Okay? You add U1 with V1, you add U2 with V2, U3 with V3, and so on and so forth. And that's the new vector that you generate by doing this addition operation. And that's the definition of how you add two vectors. Okay? The only condition is that both the vectors have to be from the same space. Okay? And the corresponding geometric operation is something again you're probably familiar with from vector algebra, from maths or physics. Okay. Imagine this red colored arrow is the V vector, and the blue colored arrow is your blue vector. The addition of these two produces a new vector U plus V. Okay. And the way you obtain U plus V is through what is called the parallelogram law of addition. Do you remember this? How do you do this? Yeah, good. Sorry? No, you have to be louder, Joe. I don't hear very well. No, hold on. Okay. If you say U square plus V square, right? We have not defined the U square operation. For the real number, you know how, if I give you 3 and I ask you what is 3 square, you know how to do. We currently don't have a definition for how you would square a vector. Okay, so the parallelogram law of vectors is simply this. If you want to add two vectors, I'm going back to 12th standard or 11th standard physics. Let's say we have two vectors like this. How do we add these two? So you essentially form a parallelogram with these two as two of the sides. You simply draw two parallel lines. At the tip of B, you draw the line parallel to A. At the tip of A, you draw a line parallel to B. These two will meet here. And if you consider this, right, this will form a parallelogram. Okay? And the main diagonal, okay, or the larger diagonal. I shouldn't say the larger diagonal, depends on the directions of the NB. This main diagonal is essentially now A plus B. Or another way to think about this is if you have A, you have B, you simply take B and you shift it along with A till the base of B meets the tip of A. Okay? and then you join the base of A with the tip of B. Shift of B. These two are the same. Okay, that's the parallelogram law of addition, right? The same thing applies here. Okay, if you have two vectors E and B like this, if you say you're adding them, all you're doing is you're applying the parallelogram law of vectors to get the new vector, which is the sum of your original two vectors U and V. Okay, that's the geometry associated with vector addition. Scalar vector scaling is simply stretching or compressing or reversing the direction of the vector without changing direction. Vector addition is simply now applying the parallelogram law of vectors to generate the new vector. Okay, the same some of the same properties of vector scaling up apply here as well. It's commutative A plus B will be B plus A. For example, that means here I moved B to a tip of A to generate A plus B. You could have moved A to the tip of B. Okay. You could have moved A to the tip of B. Yes. We're audible again. Is it okay? Yeah, sorry, we had a slight technical glitch. Is that any better? Yeah, okay. We are more closer. Okay. So in this case, we moved B to the tip of A and then found out the resulting vector. You could very well move A to the tip of B and the resulting vector would still be the same, which basically demonstrates that vector addition is commutative. A plus B equals B plus A. Okay. It's also associative. And if you add the zero vector to a vector, it does nothing. Okay. And if we can talk about subtracting two vectors, it is simply we take a vector A, multiply it by -1 and add to the original vector, and that will produce a zero vector. So you can think of this as a subtraction operation, which is simply a generalization of the addition operation where you are adding a vector to a scaled version of itself, except the scaling factor is -1. Okay. Right. Those are the two operations we will deal with when we're dealing with linear algebra. And that's incredible that with just these two operations, what all useful things you can do and what all interesting things you can do. Okay. And that brings us to the first major definition of that we will deal with in this course, which is essentially vector space. Okay. So vector space, whenever you hear the term vector space, what we're talking about is a set. When somebody says vector space, the entity that they're talking about is essentially a set. It's a collection of stuff. Okay. Then you could ask, well, why not just call it a set then? Why are you giving this special name? We give it a special name because this set has some special properties. Okay, and that is why it's it's given a special name. Okay. So again, this is something I want you to really get imprinted in your head. When somebody says vector space, we're talking about the set, which is a collection of stuff with some special properties. And now we look at what those special properties are. So, and we call, and the reason we call it a vector space is we will refer to, so it is a set, it's got some elements. If it is a vector space, we will refer to the elements as vectors. Okay. So if you remember yesterday, I said that. So I said we will start with n vectors, but vectors are more general quantities. Okay. So we define vector space for us. Anything that is an element of a vector space will be a vector. That is why functions are vectors, images are vectors, matrices are vectors, as we will see later. Okay. And it turns out these n vectors actually form a vector space. The collection of n vectors form a vector space. That's why we call them a vector. Okay. So vector space is a set. It is essentially a set of vectors. Let's say we refer to this set as by the letter capital V. Okay. This set is a vector space if it satisfies two properties. Okay. Essentially, it needs to be closed under two operations. Okay. Essentially, the two operations that we've looked at for set for vectors: vector addition and vector scaling. We know what vector addition is. We know what vector scaling is. We need to define what we mean by closed. Okay. What we mean by closed is this. Okay. I think you remember this bag of real numbers that we talked about. Whenever you put your hand inside and take an element out, you get a real number. Okay. Now, let me ask you this question. I put my hand in, take a real number out. Okay. I put my hand in, I take a real number out. I multiply that real number by some real number, some other real number that I have with me from before. Is the resulting number a real number? Yes. If you multiply two real numbers, you get a real number. It means if I look in the bag, this new number that I've generated will be there in the bag. Right? Okay. I take another number, I multiply by another real number, and if I look in the bag, it will be there. Right? If for any possible number that I can generate by doing the scaling operation, if I can find the new number in the original bag, then I would say that the set of real numbers are closed under multiplication. Okay. So similarly, if I have a n vector, okay, if I put my hand in and take out, I get a column, a vector of numbers, n numbers. I scale it by a real number. That means I multiply each of these individual elements by the scalar alpha. Since each of them is a real number, that means if I look in that Rn bag, I will find the vector there because it's simply a bag of n real number bags. Right? If this is satisfied, for any possible vector that I pull out and any possible number I multiply it with, then I would say that this set is closed under scalar multiplication. Okay? That means if I take any element, I do scalar multiplication, I will still stay in that set. I won't go outside the set. Okay? That's what closed means. Now you can similarly figure out what it means to be closed under vector addition. I have a real number bag. I take two real numbers. I add them together. And when I look inside to see if this new number that I've generated is in the bag. So it is there. So any possible two numbers that I can pick up, then I say it's closed under a real number addition. Similarly, if I take Rn, if I take two Rns, add them, and if I can find that a new n vector in a new vector in that in my bag, then I say it's closed under this addition operation. Okay. And now, if you have a set that is closed under vector scaling and vector addition, then you say that this set is actually a vector space. That is what the definition says. Okay. Now, and that's what I've written down mathematically here. Let's say we have a set V. Okay. And I take two vectors x and y from the set. This essentially means that x and y belong to V. Okay. And now I generate a new vector x plus y. I know how to generate it. Okay. And if the new vector x plus y is also found in y for any possible x and y. X and y can be anything that I can choose. If the new vector that I generate ends up in V always, right? Then I say the set is closed under vector addition. Similarly, if I choose the vector x from my original set V, and I choose some alpha, forget about this f. You don't have to worry about it. Let's say it's real number or complex number. I choose any real number and I do the scaling operation. And if the new vector that I've generated is in the original bag, original set V, then I say it's closed under vector scaling. And if both of these are satisfied, then that set that you have, that you've been working with V, it can be called a vector space. If any one of them is not satisfied or both of them are not satisfied, it's not a vector space. Okay, that's all. It's as simple as that. Okay, and this is something you have to remember. Okay. Let's see an example before we move on. Okay. By that argument, the set of real numbers, right? It's a set. Is that a vector space? By this argument. Whenever you have this question, right, you simply blindly apply those two rules. Yes or no? Yes. Because then R is a vector space. Because it's closed under, well, the definition of vector scaling and vector addition is simply vector scaling is multiplication of two real numbers, vector addition is addition of two real numbers. Okay? What about R2? Is that a vector space? It's a set. It's a set of two vectors. Yes or no? If it's yes, you have to explain why. If it's no, you should tell me why. Okay, let's look at it. If you look inside R2, right, it will essentially have all vectors of this form. The first element is a real number, second element is a real number. Okay. Now I take some element from R2. I do scalar multiplication. Okay. Means I'll get alpha times the first number, alpha times the second number. This is a real number, this is a real number. Okay. That means this is a indexed list of numbers with two real numbers. That means this has to be found in R2 because R2 is a set of all possible such vectors, such n vectors. That means if you do scalar multiplication, we will find the resulting element in R2. Similarly, if I take two vectors from R2 and I add them, I add the individual elements together. I'm essentially adding two real numbers here. Addition of two real numbers gives you a real number. That means what results is of this form. It's got two real numbers. That means this has to be found here because that's the definition of R2. Geometrically also, that makes sense because we know what is the geometry associated with scalar, vector scaling and vector addition. That means in R2. So this is R2. This is my origin. If I take any vector V and if I scale it, right? No matter how much I scale it, it will still be in that plane because this plane has infinite extent in two directions that you can move it. Right? Similarly, if I take two vectors like this and add them, the new vector will be here. No matter what vector I choose, remember these are all vectors with finite values. Infinity is not included in the real line or in real numbers. So these are finite. These are elements with finite values. Adding to finite values produces a finite value. That means that new vector that you generate has to be in the plane. Okay, that means it's closed under vector scaling and vector addition. So R2 is in fact a vector space. By the argument, what about R3? Same. We're simply extending it to 3. That means in general, Rn is in fact a vector space. Okay. See, there are several properties that vector spaces satisfy. I won't go into all of them because these are simply extensions of properties of vector scaling and vector addition. I will only add one more thing here. A consequence of this definition is that if you have a vector space V, right, this vector space will always have the zero element. For example, what is the zero element in R? So it says 0. Okay. What is the zero element in R2? No, not just 0. It's 0, 0. This is the zero element. Rm is simply the zero vector. If you want to quickly rule out if something is not a vector space, you take the set V. If it does not have the zero element, it's not a vector space. If it has, you still have to do some work to figure out. If it does not have 0, you can say no, it's not a vector space, and the story ends there. If it has 0, then you still have to go and verify, well, is it closed under vector scaling, is it closed under vector addition? maybe you're wondering, okay, what is the big deal about this closed nonsense? Right? Obviously, it's closed. From the way we define real numbers, it has to be closed. We say the plane is infinite, and when I'm essentially doing operations on finite quantities, I will generate a finite quantity, or vector scaling and vector addition will always produce, the way we define it, always produces finite quantities. That means it has to be in that set. Isn't it trivial, to tell about this closeness under vector scaling and vector addition? So the original definition was, it seems like that, but the reason this is defined, I hope will become clear once we talk about subspaces. Okay? Subspaces are again sets. Vector space is a set with special properties. Subspaces are again sets with special properties, but they have one other property. It's not just a set, it's a subset of something. Okay? Usually, this is a subset of vector space. That means you originally started with some set B, which you know is a vector space. And then you pull a small chunk out of it from B, right? And I'll call that W. And W is a subset of B. That means I've taken some elements of this original set B and I put it in W. So W is a subset of a vector space. Okay, that means it's also a set. Okay. Now we can ask, well, this property of whether something a vector space or not is something that you assign to a set. And W is a set. So I can ask, is W a vector space? It doesn't matter that W comes from another bigger from another vector space. The W itself is a set, so I can ask, is that a vector space? And how would you verify if W is a vector space? Based on what we just saw, what all would you check? What is the first thing you check? If it has a zero element. If it does not have, you say done. It's not a vector space. If it has the zero element, then you have to go and check the other two. You check whether it's closed under vector scaling or whether it's closed under vector addition. And if those two are satisfied, then W also is a vector space. Right? Okay. So that's essentially a subspace. And it is probably clear from the definition. If I have a subset of a vector space, and that subset also satisfies the properties of a vector space, then we call that subset a subspace of the original vector space. Okay, and that's essentially what I've said here. Okay, and often you might see things like this, where it does not look like vector scaling, it does not look like pure vector addition. It looks like a combination of the two. Okay, this is essentially that. So this is called the this is also another term we will often come across. I don't have it as defined in the slide, but we will define it now. Okay, a linear combination which looks like this. Okay, so the subspace is a subset of a vector space, which is also a vector space. Yeah, all right. And this definition that we have here, alpha x plus beta y. Let's say we have two vectors x and y from Rn. Okay. We know what vector scaling is. If I say I scale x by alpha, this is the operation I'm doing. If I scale y by beta, this is the operation I'm doing. If I say I'm adding x and y, this is the operation I'm doing. But these two are also vectors, right? Then that means I can add these two. Right? And whenever you do this, right, this is called the linear combination. This is the linear combination of the vectors x and y. So when I say I take two vectors and I take the linear combination, all I'm doing, I take the two vectors, I scale each one of them by a certain amount and I add them together. Okay. So we could go back and slightly change the definition of vector spaces and say, well, vector space is a set which is closed under linear combination of vectors, which essentially means it's closed under scaling and vector addition. Because scaling and vector addition are special cases of this. Right? If I set beta to 0, then I'm essentially just scaling x. If I set alpha to 0, then I'm essentially only scaling y. If I set both alpha and beta to 1, then I'm simply adding two vectors. Right? So think of linear combination as a generalization of scaling and vector addition. And that's essentially it. And all the operations that we will do with vectors are simply linear combinations. All right. Now we come back to this definition of a subspace. Okay. Let's say we keep it R. Okay. We can represent this space as a line, right? The real line. Okay. And if I choose one point here as a zero element, you can represent every other vector in R through an arrow pointing from starting from 0 and ending at the location of that point. So we know R is a vector space, right? Let's say we choose a small subset, of R. I'm going to say, well, I'm going to generate a new set called W, which is simply this. All the elements from 0 to 1, including 0 and 1. Okay, that's essentially this. I'm not considering this entire line, which I know is a vector space. I consider only that small segment, line segment from the real line. W is a set. It's a subset of a vector space, so I can ask, is it a subspace of R? How would you verify? Well, it's a zero element. So no help there. We'll have to do more work. So we need to verify whether or not it's closed under superposition of vectors. See, to disprove something, you only show that it fails in one condition. So to prove something is a little harder. So to disprove, if you can show that there are examples that you can find where either vector addition or vector scaling does not fail or is not closed under vector scaling and vector addition, you're done. Then you say it's not a vector space. Yeah. So, okay, let's do this. Let's say we take some element, let's say 1, right? Then it's easy. We want to do scaling. If I multiply it by a number alpha, which is positive and less than 1, is the resulting number in this set W. That means then we could say it's closed. Well, if alpha is 0.7, I'll get 0.7, and 0.7 is in the set. But what if alpha is 2? I get 2, I go, so done. It's not a vector space. Okay. I choose another one. Minus 100 to plus 100. Is that a vector space? 0 is there. So you have to do test. It's a vector space. 0 element is there because it includes 0. Is it closed under vector scaling? No, you take 100 multiplied by 2, you're out of the set, so it's not closed, so it's not a vector space, okay? You don't have to think too much. It's not. It doesn't have a 0 element, so it's out. So it's not a vector space. So now maybe the concept of closedness becomes a little clearer. Right? Maybe if I consider the entire space, of course, it seems obvious that it's closed. Right? But if I take small segments of it, then it's possible that if I do this linear combination of elements from a small set, I might go out. Okay? And this idea of going out, again, we'll see later why it's important, because it has a geometric meaning. That's why this closedness is important. It might seem trivial for the full space Rn, but if it takes small elements of Rn, then this property of closedness makes sense. Okay, I have a small part of Rn, and I want to be able to do linear combination of elements from that small part of Rn and still stay in that small part. So that's where closedness becomes relevant, at least in the context of subspaces. It's not as trivial as what it seems like when you consider the full space. Okay. Now let's maybe I'll ask you this. I have I. I found okay, which only has a zero element. And the curly brackets simply mean that's the notation used for representing a set. This square brackets essentially say they are closed intervals on the real line. This is my set. Simply the zero element. Is that a subspace of R? Again, blindly apply the rules. Check zero, check closeness under addition and scaling. That's zero. Fine. I will need to test. To close under scaling? Yes, you take zero, you multiply by any number, I get zero, so zero there. What about vector addition? Why not? 0 plus 0 will give me 0. No, so you can take, okay. Imagine you can take from the bag. If you're taking a copy from the bag, you're not taking the thing out of the bag. I can take 0 as many times as I want. If I add, I'll still produce 0. So that means if you have a set that only has a 0 element from a vector space, that is always a subspace of your original vector space. And this is often called the trivial subspace. Okay, that's what I have in the next slide. Okay. Maybe real line is okay, but it's maybe not that interesting. Let's maybe look at R2. Maybe that's a little bit more interesting than just the real line. If we're dealing with maybe because we're used to seeing the Cartesian coordinates, let me just draw it. This is R. Okay. I know this entire space is a vector space. Okay, all of R2. Okay. What if I take a subset of R2, which is like this? Essentially a straight line that is passing through the origin. Okay. Now I call this W. W is a subset of R2. So I can ask, is W a subspace of R2? If you say yes, you have to explain. If you say no, you have to explain again. Does it have the 0 element? It does, because I've drawn it as if it's passing through the origin. So fine, we have to now check if the scaling applies. I've not given you the exact analytical expression for the line, so algebra won't help here. We should do the geometry. We should use geometry to verify whether vector scaling and vector addition applies here. And it's closed. Is it closed under vector scaling? Yes, no? Yes. So if you choose if I choose an element from W, right? Let's say I choose this vector. I choose this vector. If I say I'm doing scale operation, I'm not changing the direction. I'm simply stretching it or flipping it. I'm essentially just stretching it in that direction. I might reverse the direction, but I'm simply stretching or compressing it in that direction. That means if this is, let's say, x, if I do alpha times x, right, it has to be along that line, right? Because that's the geometric version of your scalar multiplication operation. Right? That means if you have a straight line passing through the origin, it is closed under vector scaling. Okay? What about vector addition? Again, take the vectors along that line, in that line. If you add them, will you stay in the line? Even if you're not here, apply the parallelogram line vectors. Move one vector to the tip of the other vector and see if the resulting vector is on that line. If you're not able to do it in your head, do it on the paper. Take two vectors, move one to the tip, and then tell me if the new vector that you get also stays in that line. Are you sure? Okay, let's see. Okay. I have X. Okay. And let's say I have another one which is slightly longer. This is W. Remember, W starts here and X. This is W and this is X. So we call it Y. If I add X and Y, what would I do? So I have X like this. I'm drawing it parallelly, but these two are the same point. This is Y. If I want to add X to Y, right, I simply take X, move it along Y, and place X here. And then this new vector starting from here to here, that is my X plus Y. Is it pointing in the same direction or no? It is. So in that case, it is closed under vector addition. If I take two vectors here and I add them, is a new vector in the line or not? It is. For example, you can also verify that if you take another vector here, right? The resulting vector will always stay in that line. Okay? That means if you have a line passing through the origin from R2, that subset is actually closed under vector addition also. That means this set W is actually a subspace of R2. It's not just a subset of R2. It's a subspace of R2. Is it clear? Okay. Let's look at another example. What about this? The other line passing through the origin. Is this a subspace of R2? I'll call it B. Yes, it doesn't matter. The argument we had is independent of direction, right? So it means any straight line passing through the origin in R2 is actually a subspace of R2. Okay. Fine. I call this V. This is R2. Circle F radius 1. Okay. Now I ask you, is it a subset of R2? It is a subset of R2. The elements of V are all in R2, so it's a subset of R2. Is this a subspace of R2? No, right. So, if you want simpler, what is the first thing you test? Does it have the zero element? See, the elements of V are only the black points on the black line. Nothing else is in V. Obviously, no, this is not. Okay, all right, let me make it anything inside I want a circle disk. I give you a disk. Is this now I ask you, is a subspace of R2? Okay, that's it. Yeah. This has a mind of its own. Okay. Let's say let's take 2 points. Okay, it's gone again. Okay, it's better than that. So let's say this is origin. Like this is what you meant. This is what you meant. We take 2 points. Okay. If you assume that the new set that we're dealing with, let's say, is the disk. This means everything inside the circle, not just a circle. It's a disk. Are you closed under scalar multiplication? That's the question. Think about it geometrically. Okay, let's say we take this vector x. What do I do when I do scaling? Geometrically. No, geometrically, what am I doing? We're stretching or compressing or reversing the direction. Is there stretching that you can do to this x such that you go outside the disk? Really? Okay, I take x. What if I keep stretching it? I can obviously take it beyond the disk, right? You can do any amount of stretching. Is that right? No. Right, so here, I have a disk, I have a point. I have the freedom to stretch the point or compress the point as much as I want. That means I can obviously go outside my disk, right? That means I can, if I can choose, let's say I can generate this vector along the same line by choosing some alpha. If I choose alpha to be large enough, right? I can always go outside the disk. That means any finite sized disk in R2 is not a subspace of R2. You don't even have to check for vector addition. All you have to do is only check for scaling. So vector addition is easy to show. If you choose two vectors at the edge of the disk, if you add them, obviously the new vector is going to be this. It's outside. So the disk is not closed. Right? So that means now you have examples where things are not closed. So you can have pure subsets and not subspaces of R2. Okay. Now we look at what is so special about this scaling and vector addition business, or this linear combination business. Geometrically, I know that straight lines passing through the origin are subspaces of R2. Okay. But if I had something like this, so if this is x1, this is x2, this is essentially x2 equals x1 square, a parabola. Okay. Is V now a subspace of R2? Okay. Geometrically, let's verify. If you say you're choosing a point, right? Let's say I'm choosing this point. In V, that corresponds to this vector. Okay. It has a zero element, so there is no help to us. I'm going to call this vector x. If I scale this vector, do I still stay in the curved line corresponding to the parabola? No. Even if I do a slight bit of scaling, I will always move out of the parabola. That means this is not a subspace of R2. Okay. What is one obvious difference between, so the red lines here were subspaces of R2, whereas this line or the circle was not a subspace of R2. What is one obvious difference between them that you can immediately see? Not linear, but you are in the right direction. What is the difference between the black subset here and the red subset here? Sure. Or if you look at the red lines, right, they are flat, right? Whereas the V1 is curved, right? And that is essentially the core of linear algebra. Linear algebra is simply one way to think of linear algebra is a study of flat spaces in higher dimensions. That's all this whole thing is about, geometrically. Right? And this business of being closed under vector scaling or vector addition or linear combination is essentially, so this linear combination is an operation that will keep you in a flat space, or it can only generate points from a flat space. It cannot produce curved surfaces for you. It can only produce flat spaces. And in linear algebra, whenever we're talking about the geometric view of linear algebra, we're always talking about doing stuff in flat spaces in higher dimension. Okay? So, flat spaces or surfaces on R2 are these lines. Okay? What about R3? R3 is difficult to visualize on this tablet, but we have the space. Okay. Let's say this is the origin, X, Y, Z. We have the origin at the corner of the room. Right? R3 is vector space. Can you give me examples of subspaces of R3? What about lines passing through the origin? Yes, flat, infinite extent, it's fine. What about planes passing through the origin? That will turn out that those will be subspaces of R3. What about the sphere? Actually, it's not. Anytime you have any curvature, you're done. It's not a flat surface, so those will not be subspaces of R3. You simply imagine that you can visualize these things in dimensions higher than 3. So you say Rn, if you have a bunch of vectors and you're taking the linear combination, let's say you take all possible linear combinations, you'll then generate a whole bunch of infinite number of points. It will turn out that those points will always lie on a flat surface. Okay, it will never produce curved stuff. So that's the speciality of linear combination. Okay, and that's essentially what I said here. All planes and all lines passing through the origin of R3 will be subspaces. Okay, but there is one little caveat. Okay, that we need to be careful of. R2 flat surface. I'm calling it a surface. I'm using surface as a general term. This is, of course, a line, but surface is a general term for lower dimensional stuff in high dimensions. Okay? Is V a subspace of R2? No. It's flat, but it's not. So, for something to be a subspace, of course, it has to be flat, and it has to pass through the origin. Okay? And you can verify this using our definitions. Okay, not just rely on this heuristic of is it flat. If I take this vector, right, and I scale it, I will go outside the line. Okay, so this condition of checking for 0 is a consequence of not being closed under linear combination. Okay, it's not a separate rule by itself. It's just a rule that is quick to check. That's why I say keep that in mind. Okay, if you verify scaling, it's not satisfied. That means it's not a vector space. The quicker way to do that is 0 is not there, so it's not. Okay. Right. See, everything that we discussed so far geometrically can be done algebraically as well. So if you go to the course notes, at least the first chapter is complete. You will have examples there where we show that the parabola here, this curved line, is not closed under vector scaling and vector addition algebraically also. Here I'm only talking about it geometrically, but you should go look at it algebraically, because often when you're working out stuff, especially in higher dimensions, you can't draw pictures and figure out. You have to be able to do the algebra. Okay? The geometry is essentially to help you get the intuition, but finally you still have to do the algebra by hand. Okay, all right. Yeah, two important definitions of vector space, subspace. Okay? And I hope the geometry behind these two are also now clear. The next, again, a very, very important definition is linear independence. Okay, and the definition is again a little weird. Okay, but the geometric intuition is relatively easy to grasp. Okay, and linear independence. So vector space and subspace are sets special properties. Okay, linear independence is a property of a set of vectors. Okay, so this is linear independence. You should remember it's a property of a set. Okay, it's not a set. Linear independence is not a set. It's a property. All right. So we say that the collection of set of vectors is independent. Okay. Okay. All right. If it's not linearly dependent, okay, I'll say what linearly dependent means. Okay. A set of vectors. Let's say you have a set of vectors x1, x2, xn. Okay. And we'll assume each of these vectors is from Rn. It need not be. It could be from any vector space V. Okay. But for now, for simplicity, we'll assume it's from Rn. We have a set of n vectors. Okay. And we do a linear combination of these vectors. And what that simply means is you take each of those vectors, multiply each one by a scalar. Okay. So you multiply x1 by some value alpha 1, x2 by some alpha 2, xn by alpha n, and then you simply add all of them together. Okay. And then you will produce another vector v, y. That's it. Okay. This is the so this here is the linear combination of the set of vectors that we started with. Okay. And that produces a vector y. Okay. You say that a set of vectors is linearly dependent. Okay. If you take the linear combination and you want to produce this zero vector. Okay. You say that the set is linearly dependent or linearly independent if the only way you can produce the zero vector through a linear combination is by setting all the alphas to 0. If any one of the alphas is non-zero and the linear combination still produces a zero vector, then you say that the set is linearly dependent. Linearly independent means the only linear combination that produces the zero vector is when all the scalars has to be 0. Okay. If only one of them is non-zero, then you say the set is linearly dependent. Okay. So, let's again do some examples. You can just remember this for now. This is very important. Okay. Let's take R. Okay. Let's say I take a small set of R. One small subset of R, 5. I'll call it, let's say, 5 is from R, so this is a subset of R. I ask, is V a linearly independent set? If that is the question, it's very simple. All you have to verify is you take the linear combination of the elements of the set, and if the only way you can produce a zero vector is by setting all the alphas to 0, then it's linearly independent. If there is any other possible combination with alpha that will produce a zero vector, then it's a linearly dependent set. Okay. So if we want to do the linear combination of these sets, of the elements of this set, then the only possible linear combination is alpha times 5. Okay. And we want to produce 0. 0 is the zero element of R, 0. What are all the possible values of alpha that we produce, that will satisfy this equation? 0. There is no other alpha that I can choose that will equal to 0. That means alpha has to be 0. That means, what can we say about this set? Alpha is 0, but this set is linearly independent. That means the set that I have with just one element 5 is linearly independent. Okay, right. Now I form another set. I'll call it W. Okay. Now I ask, is this set linearly independent or dependent? Okay, well, very simple. You take a linear combination. Well, any linear combination will look like this. 5 alpha times 5 plus alpha 2 times 1, and I want to produce a zero vector. What possible values of alpha 1 and alpha 2 can I choose that will produce a zero vector? 0, 0 will obviously give you 0. But is there another combination that will produce the zero vector? Yes. If I choose this as minus 1, this is 5, that will produce a zero vector. That means there is a non-zero combination of alphas that will give me the zero vector. That means this is linearly dependent and it's not linearly independent. Okay? What about this? What about this set? Is it linearly dependent or independent? Independent? So you got to be louder. I don't know what you're saying. Do the same thing that I've done. What did I do to figure out? So for this, how did I figure out? Yeah, so there are non-zero combinations of alpha 1, alpha 2, alpha 3 that you can choose to produce a zero vector. That means this is not independent. This is again a linearly dependent set. Okay? I'll give you another one. It is linearly dependent or independent? Yeah, so that means I can choose non-zero alpha that will give me 0. So here is another quick news. Set, and if the set has a zero element, you immediately make linearly dependent set. Because you choose every other alpha to be 0, you simply choose the alpha corresponding to the zero element as a non-zero value to produce a zero vector or a non-zero combination of alpha. That means it's linearly dependent. Okay, right. So this is easy for R. For R2, maybe it's the algebra might not be trivial, okay, or the computations might not be as simple as case of R. Okay? But we look at the geometry associated with linear independence. Okay. Okay. In the first case, right, this had only one vector. The set had only one vector. So this is the vector corresponding to 5. This is 0, this is 5. Okay. And the only way you could produce a zero vector is by multiplying the vector by 0. That's the only thing that will squish it to 0. Okay. For the second case, you have two vectors. You have 5 and you have 1. Okay. You can squish both of them to 0, or you simply take 1, scale it by minus 5, that will produce this vector. Minus 5 times 1. And if I add this vector with 5, I'll produce a 0. That means I could produce a 0 vector without switching everything to 0. Right? So in the real line, whenever I had more than one vector from the real line, there is always a non-trivial way of producing 0 without squishing everything to 0. If I only had one non-zero element, like in the first case, like 5, the only way I could produce a 0 vector is by squishing it to 0. Okay. Another way to state this is the following. Okay. If you have a set that is linearly dependent, okay, it simply means that there is some redundancy in your set. Okay. There is more, one way to think about this informally is somehow there are more elements than the amount of information conveyed by your set. Okay. Imagine each vector conveys some information and each one conveys some unique information. Okay, that is not present in the other ones. In a linearly independent set, each element of the set has something unique it offers, which I cannot get from any of the other vectors, other elements. Whenever you say you have a linearly dependent set, there is at least one vector whose information can be obtained from the other elements in that set. Okay. So, linear dependence and independence simply has to deal with is it set redundant or not in some sense. Okay. And more specifically, what this means is whenever you have a linearly dependent set, there is at least one vector that you can express as a linear combination of the other vectors. Let's take the example of the second example, 5 and 1. Okay. I know that alpha 1 times 5 plus alpha 2 times 1 is 0 for non-zero alpha 1 and alpha 2. Right? So, that means now I can express 5 by appropriately choosing alpha 2 and alpha 1. I can get 5 just from 1. I do not need 5. I could have produced 5 through a linear combination of by doing linear combination with just 1. So that's essentially what it means. I can, if your set has an element which could be produced through linear combination of other elements in the set, then that set is linearly dependent. If the set has elements that cannot be produced by linear combination of other elements in the set, then you say it's linearly dependent. See, in the real line, we could understand the geometry. Okay. Let's look at it for R2. R2. Let's say I choose this vector x as my set. So my V is non-zero vector. Is this set linearly dependent or independent? See, whenever you have a single element in a set, it's not zero, it's linearly independent. Okay, because the only way I can produce alpha times x equals 0, and if x is non-zero, alpha has to be 0. So it's linearly independent. Okay, all right. So why? If you the new set that I'm dealing with V. Now I ask, okay, is this set linearly dependent or independent? So it's not clear. Okay. Let's look at it slightly differently. We said a set is linearly dependent if you can produce at least one of the elements as a linear combination of other elements in the set. Okay. We can show that this set is linearly dependent if you could have produced y through linear combinations of x, or you produced x through linear combinations of y. If you could do any one of those, then it means it's a linearly dependent set. But if there is no linear combination of x that will produce y, or no linear combination of y that will produce x, then you have a linearly independent set. Okay. Now, if you have two vectors x1, two or more vectors x1 and x2, you know what the linear when I say I'm taking a linear combination of x1 and x2, you know what that means. It means I'm taking x1, multiplying it by some alpha 1, and then I'm adding it to alpha 2 times x2. If I have only one element, and I say I'm taking a linear combination of that element, what am I doing? All I'm doing is I'm only multiplying it by some scalar. That's it. No addition. There is nothing to add. It's only one vector. For a single vector case, linear combination simply means you're multiplying it by alpha. Some alpha. Okay. With that in mind, to verify if this is a linearly dependent or independent set, all you have to check is, can linear combinations of x produce y? Okay. And linear combinations of x simply means scaling x. What are all this set of vectors I can produce by simply scaling x, by doing linear combinations of x alone, geometrically? You can produce 0. If you multiply x by 0, you produce 0. But what are all the other possible sets I can produce geometrically? Can you tell me geometrically from this? Yeah? No, right? See, if I take x, right? If I multiply by 1, I get x. If I multiply by 0.5, I get a point that is halfway between 0 and x. If I multiply by 2, I get a point that is twice as distant as x, but in the same direction as x. That means by simply changing alpha between minus infinity to plus infinity, I can produce all points pointing along the direction of x. Right? That means linear combinations of x will produce all these points. The red line that I've drawn is essentially all the points you can produce by taking linear combinations of x. Does it contain y? No, here. Look at the graph. Does it contain y? Does the red line contain y? No, it does not. The point y is here. It does not contain the point y. That means you cannot produce y by simply taking linear combinations of x. What about the linear combinations of y? What will they look like? Well, they will be these points. And x is here. If you simply take linear combinations of y, these are all the things you can produce. X is not in that line. That means x cannot be produced through linear combinations of y. That means this set has to be linearly independent. This is a geometric argument. You can show all of this algebraically. In fact, you'll see that all of these concepts are related as we go later. The rank of a matrix, linear independence, all of that is related. Okay? So in this case, it looks like they are linearly independent. Right? And this geometric argument that you've done, right, is equivalent to saying there is no possible linear combination of x and y that I can take that will produce a zero vector without setting both alpha 1 and alpha 2 to 0. Okay? That is equivalent to saying y is not in the linear combination with x is not in the linear combination with y. For this two vector example that I've shown here. Okay? Let's look at another example. This is x. This is y. X and y are collinear. Okay. Now I form a set. Now let's go back to the set. V. Is this a linearly dependent or independent set? In this case, it's dependent. Because if you now take all the linear combinations of x, right, that will be this line. That includes y. That means I could have simply produced y by simply scaling x by an appropriate amount, and I could have produced y. That means there is redundancy here, at least in terms of linear combinations. Okay? So this is a linearly dependent set. Okay. So another way to think about this is, at least in R2, if two elements of a set are collinear, right, then for sure it's linearly dependent. Whenever you have non-collinear vectors, then you have linear independence. And it just turns out that in R2, and we will see later, that whenever you have three vectors, it will turn out that set is always linearly dependent. Okay? But we'll come to that later. So the same argument applies in R3, geometric argument. In R3, so choose one non-zero vector, it is most likely to be, it will be linearly independent. If you take two vectors, as long as the two vectors are not collinear, that set is still linearly independent. If I take the third vector, and the third vector is not in the plane containing the first two vectors, it will still be linearly independent. Okay? But if the third vector lies in the plane that is contained, that contains the first two vectors, then that will be a linearly dependent set. Or if any of the two vectors are collinear, then you again have a linearly dependent set. Okay? All right. Okay. But then we've already looked at this a little bit. Bring us to this next idea called the span of a set of vectors. Okay. As I said before, vector spaces and subspaces are sets. Linear independence is a property of a set of vectors. And span now is another set. Okay. It's essentially a set that is produced by another set of vectors. Okay. And the idea is very simple. If you have a set of vectors, V1 to Vr, okay, from Rn, we say, we'll always assume it's from Rn. Okay. We have a bunch of vectors. We can take linear combinations of these. Okay. If I write down the linear combination like this, then so choose alpha 1, alpha 2 to be specific values, I'll produce one more vector, one new vector, right? But if I change the value of alpha 1 to alpha n, I'll produce another vector. Now, this set is all vectors that I can produce by simply choosing all possible combinations of alpha 1 to alpha r, which is essentially the span of a set of vectors. Okay, that's what I've written here. The span of S. Okay, S is the original set that you started with. The span of that set is simply all possible linear combinations of elements of this original set S. Okay. We already discussed this idea as a span when we talked about linear independence. Here, if you had a set S that only had X, okay, then I could ask, what is the span of X? What would you tell me? Well, the definition of span is linear combinations of elements of that set. X is the only element. The linear combinations of a single element are simply the different scaled versions of the same element, and that is essentially this red line that we produced. Okay? This red line is essentially the span of the set X. Okay? Another way to think of span is I have a set of vectors. What all can I produce by simply taking linear combinations of the set? That's the span. Okay? Similarly, this blue line that you have there, that is the span of the set containing this line. Okay? Is it clear? Okay. So we started with a set and we produced another set which we're calling the span is also a set. Okay? If it's a set, then I can ask, is it a vector space? Right? Because vector space is a set with special properties. If the span of a set of vectors is a vector space, what would you have to verify? What would you do to verify? Three properties again. 0. Right. Does the span of a set of vectors have the 0 element? Right? Yeah. Exactly. See, it's all possible linear combinations. If I simply choose all my alphas to 0, I'll put it 0. That means the span of a set of vectors will always have the 0 element. Okay, that's done. But still, we need to now verify the other two. Is it closed under scaling? How? No, that's not okay. Okay. You should go back to the original definition of what a span is and then verify that whatever you're saying is satisfied under those constraints. Remember, we've not talked about the geometry of a span of vector. I've only shown you the algebra. Right? Okay. Okay. We started with the test, right? Yes. Okay. The elements of span of S are of this form. Okay? Every element of this set of span of S will be of this form. Correct? Because that's the definition. That means if I take an element from span of S, right? I'll call it, let's say, X. Right? It will be some, I'm going to use a simplified notation so that I don't have to write this again and again. No. Sorry. It will be of this form. Okay, and I've simply written down the summation like this. Okay. I know the zero element exists. Next thing I want to test is scaling. When I say I'm scaling X, right? That means I'm multiplying this by, I will not use alpha because I've already used alpha. I'm going to use, let's say, gamma. And when I multiply X by gamma, that means I'm multiplying this whole thing by gamma. And vector scaling is commutative. It doesn't matter if I put the alpha before or the gamma before or after. Right? And it's also distributed. Right? I can take it inside. That means I, alpha I, gamma, right? This thing here, that's a product of two real numbers. That means this is also some real number. Okay? That means the scaled version, gamma times X, where X was a linear combination of your VI's, produces another vector, which is also a linear combination of VI's. Because here, this is a real number. If this is a real number, that means we are taking the linear combination of VI's. If the resulting vector is a linear combination of the VI's, it has to be in the span of S, because the span of S contains all the linear combinations of VI. Okay? Okay. Okay. Let's do a simple example. Let's say we only have two elements. This is our S. Okay. Talking about span of S. 5 times V1 plus 3 times V2 is in the span of S. Right? That's the definition. Because all linear combinations of V1 and V2 are in span of S. If I multiply this by -1, some scalar, I will produce -5 times V1 minus 3 times V2. This is the new vector that I produced by doing scaling. And I want to check if my set is closed under vector scaling. That means this new vector that I produced has to be, so this vector came from span of S. I've done some scaling. That is the result. This is the result. And I want to check if this resulting vector is in the span of S. But if you look at this, right, this is simply a linear combination of V1 and V2. I've simply chosen different scalar, but it's still a linear combination of V1 and V2. That means it has to be in the span of S. Okay? That means this span of S is closed under vector scaling. Okay? Let's do vector addition. Let's say we take this 5V1 plus 3V2. That's one of the vectors that we've taken. Let's say another vector we take is -1V2 plus V1, 2V2, and these are the two vectors that we've taken. And if we add these two, what will we produce? The sum of these two will be, so we can add the V1 element and the V2 elements. This will be, both of these came from span of S. We've now produced another vector which is a linear combination of V1 and V2. That means this also has to be here. So that means it's closed under vector addition also. So I've taken specific examples to show this is not how you show that it works in the general case. What I've shown here is that it's closed for this specific example that I've taken. I've not shown you in the general case that it's always closed. You could argue, well, if you choose another vector from S, then it's not closed, right? So this is not a proof. It is just to make this argument that I made maybe less abstract. That's all. But this argument in general, because I've not chosen a specific value of alpha 1 and gamma. Okay. So this span of S is in fact a vector space. And in fact, the span of S, so remember the original vectors, right? V1 to Vr were from Rn. So we found out that the span of S is a subspace of Rn. Because everything that you produce will be in Rn. So span of S will be a subset of Rn, but it's also a vector space. That means there has to be a subspace of Rn. This simply brings us to the idea that if you have a bunch of vectors and if you take their linear combinations, what you produce by through these linear combinations are flat spaces that pass through the origin. And the example is this: if I started with just x, I produce a line that passes through the origin, straight line that passes through the origin. That means I produce a flat surface that passes through the origin, which is a subspace. If you in R3, if I have a single vector and I take look at the span of the vector, it will be simply a line that passes through the origin, flat space passing through the origin. If you have two vectors in R3 and I take the span of those two, it will simply be the plane containing those two vectors which passes through the origin. So, in higher dimensions, you can essentially produce higher dimensional planes. If you're talking about R square and you have one vector, the span of the vector will be a one-dimensional plane in R4. If you have two vectors, you will produce a two-dimensional plane in R4. If you have three vectors, you can produce a three-dimensional. I say you can because you can also produce something lesser, but you can essentially produce, if you appropriately choose the three vectors, the span of those three vectors will be a three-dimensional plane in R4. Okay? Okay. Again, see, if this is a little difficult to grab compared to maybe the definition of vector space, that's essentially the nature of this material. That's why I say you have to go and be very clear about those basic definitions before you get here. Because as we move further, you're going to be building on these things. So later on, I might just say span of this and then move on. If you're not sure by then what span really means, then it's going to be a lot more difficult to grasp ideas. So please go back and review these before you come back to the next class. Okay? We'll definitely upload the videos for both these lectures by today. So that means you have one day to review and be familiar. And I would also encourage you to read the notes. At least for this chapter, it's complete. So please go and read the notes and work out the examples that are there in the text. Okay. Actually, this should be something else. The title is not correct. That's okay. Okay. We'll look at another definition. Okay. You know what a subspace is? Okay. Time with it. Yes, I lost 15 minutes yesterday, so I don't want to look at. Okay. In R2, we know that these are subspaces. Okay. This is a subspace. This is a subspace. We know how to add two vectors. We defined addition of two vectors in R2. If I give you two vectors in R2, we'll simply apply the parallelogram law of vectors to produce a new vector. It turns out we can also define addition of subspaces in R2. The definition is again very simple. Okay. If you have two subspaces, S1 and S2, and I'll usually write it like this. If you have two subspaces S1 and S2, which are subspaces of some parent vector space V, okay, the sum of those vector spaces, well, I've used X and Y. X and Y are subspaces of some parent space V. We define the addition of two subspaces as simply this. It is the set of all set of additions of all combination of elements from X and Y. Okay, that's essentially what I've written here. So S1 and S2 or X and Y are subspaces or sets. We're now defining an operation that's essentially addition of these two sets, which will produce another set. Okay. And that set is given by this. And the new set that you produce is simply this. This is X, this is Y. You choose one element from X, you choose one element from Y, you add them together, and then put them in X plus Y. You take these two, you add them, you put the result in X plus Y. You choose another element here, another element here, you add them, put it here. Another element here, another element here, add and put it here. X plus Y then essentially contains the sum of all possible vectors from X and Y. That's it. Okay. And it turns out, again, you can demonstrate this, that the sum of two subspaces is also a subspace of your original parent space Y. Okay. So here, S1 and S2 are subspaces of V. So it turns out S1 plus S2 will also be a subspace of V. Okay. Correct. I'm going to stop here. Okay. We have 5 minutes. If there are any questions so far, we will discuss them. Then we'll take it up on Thursday. Okay. 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 So everything from people online. Okay. Follow. If there's nothing else, then we'll stop here. And I'll see you guys on Thursday. Okay. Thank you.